Assalamualaikum and a very good morning to Sir Salihuddin. So today our group is from group 4D electronic packaging. We will present on fourth wave MEMS, and this is our group member. So we have Muhammad Azamuddin, Nurul Afifah and me Sharina, and then Muhammad Farhan Shalan and Robert Raj.
Okay, so I'm gonna present the introduction part. So MEMS is integrated micro devices or system combining electrical, mechanical, fluidic, and optical component and all physical domains. MEMS are fabricated using the integrated circuit IC compatible batch processing techniques, which range in size from micrometer to millimeters. This system merged the competition with sensing and actuation that change the way we perceive and control the physical world. MMS, in its broader definition, is a set of miniature technologies that make it possible to mass produce large number of integrated sensor, actuator, and communication system that can be embedded within products or spread throughout the environment. Miniaturization of mechanical system promises unique opportunities for new direction in the progress of science and technologies. Microchemical devices and systems are inherently smaller, lighter, faster, and usually more precise than their macroscopic counterpart. However, the development of micromechanical systems appropriated fabrication technology that enable the futures, such as the definition of small geometries, precise dimensional control, design flexible interacting with control electronics, repeatability, reliability, and high yield and low cost per device, which enable the MEMS advanced technology for the system of the 21st century.
Today I will talk about history of MEMS or microelectronic mechanical systems. 1947 invention of the point contact transistor, germanium. Transistor controls a bigger change in current or voltage by using electrical current or a tiny amount of voltage. Transistors are the fundamental components of computers, cellular phones, and other contemporary electronics. In 1947, William Shockley, John Bardeen, and Walter Britton of Bell Laboratories built the first point contact transistor. The first transistor used germanium, a semiconductive chemical. It proved the ability to construct transistors out of semiconductive materials. 1954 Discovery of the piezoresistive effect in silicon and germanium. C. A. Smith discovered the piezoresistive effect in semiconductor materials like silicon and germanium in 1954. The geometrical piezoresistive effect of semiconductors can be several orders of magnitude greater than geometrical piezoresistive effect of metals. This breakthrough was significant for MEMS since it demonstrated that silicon and germanium could detect air or water pressure better than metal. 1958 Invention of the first integrated circuit IC. Prior to the introduction of the integrated circuit, the size of transistor was limited. They have to be linked to cables and other electronic devices. An integrated circuit IC is made of transistor, resistors, capacitors, and wires. If the circuit could be built entirely on a single substrate, the entire device might be made smaller. In 1958, Texas Instruments Jack Kilby created an all-in circuit using a single germanium chip, one transistor, three resistors, and one capacitor. Shortly after, Fetch Semiconductor's Robert Noyce invented the first transistor on a silicon chip. There is a unitary circuit. Robert Noyce received the first patent in 1961. 1959, There is plenty of room at the bottom. The presentation popularized the advancement of micro and nanotechnology. Feynman pioneered the idea of controlling matter on an atomic scale, as well as denser computer circuits and microscopes that he viewed objects smaller than scanning electron microscopes in the 1950s. He challenged his audience to design and build a miniature engine or write information from a book page on a 1/25,000 scale surface. He provided $100 rewards for each task. Since 1997, the Feynman Prize in Nanotechnology has been awarded by the Forsyth Nanotech Institute. 1968, the resonant gate transistor patent. Harvey Denson of Westinghouse created the first batch-fabricated MEMS device in 1964. This device, known as a resonant gate transistor, combined a mechanical component with electrical features RGT, or got resonating. Most gate construction was used in the RGT. It was around 1 millimeter long and responded to a very limited set of electrical input signals. It functioned as a frequency filter for integrated circuits. The RGT was the first tiny electrostatic actuator demonstration. It was also the first time surface micromachining techniques were demonstrated. 1971 invention of the microprocessor. 1971 Intel publicly introduced the world's first single-chip microprocessor, the Intel 4004, powered by the Busicom calculator. This invention paved the way for the personal computer. 1960s and 1970s proliferation of back-edge silicon wafers used as pressure sensor. H. A. Wagner's paper "Electrochemically Controlled Timing of Silicon" demonstrated anisotropic etching of silicon utilizing a bulk micromachining procedure that removes silicon selectivity. Bulk micromachining removes the majority of silicon substrate, leaving just the required geometries left. Kurt Peterson of IBM's research laboratory created a micromachine pressure sensor using a silicon diaphragm. In the 1970s, in blood pressure monitoring devices, thin diaphragm pressure sensors have proliferated, one of the early commercial successes of microsystem devices. 1979, HP Micromachine Inkjet Nozzle. Thermal inkjet technology was created by Hewlett-Packard. The TIJ quickly warms in, causing the smallest bubbles to form. When the bubbles burst, the ink squirts off out of a series of nozzles onto paper and other medium. The nozzles are made using MEMS technology because the nozzles are less than 100 micrometers in diameter. They may be closely packed for high-resolution printing. New TIG applications, including as direct deposition of organic compounds and biological materials like sDNA, have also been developed.
In 1982, LIGA process was introduced. LIGA is an abbreviation for X-ray lithography, electroplating, and molding. LIGA was created in the early 1980s by the research center in Germany. It enables the production of high aspect ratio microstructures, which is thin and tall. Liga structures have accurate dimensions and a smooth surface. In 1986, IBM was created a micro device known as the Atomic Force Microscope (AFM). The force applied on the tip or probe of a microscale cantilever is measured by the AFM to map the surface of an atomic structure. The cantilever is often made of silicon or silicon nitride. It is a scanning probe microscope with great resolution that can see at the atomic level and generate three-dimensional pictures. So there are other developments in the 1980s. In 1988, the first rotary electrostatic side drive motors were made at UC Berkeley. And in 1989, a lateral comb drive emerged where structures move laterally to the surface. In 1992, it was created a grating light modulator. Soga invented the deformable grating light modulator (GLM) in 1992. It is an MOEMS, which is Micro Opto-Electromechanical System (MOEMS). It has been designed for use in a variety of applications, including display technology, graphic printing, lithography, and optical communications are all examples of optical communications. And then in 1993, Microelectronics Center of North Carolina (MCNC) created MUMPS, which stands for Multi-User MEMS Processors Images. So a foundry meant to make microsystem processing highly accessible and cost-effective for a large variety of users, and a three-layer polysilicon surface micromachining process. In 1998, Sandia National Labs developed Summit IV, Sandia Ultra-Planar Multi-Level MEMS Technology 5. This process later evolved into the Summit V, a 5-layer polycrystalline silicon surface micromachining process. In 1993, Analog Devices was the first to mass produce a surface micromachine accelerometer in 1993. This accelerometer was employed in autos for airbag deployment sensing by the automotive industry. It was priced $5. TRW micro sensor were previously priced at $20. It was extremely dependable, tiny and affordable. It was sold in record quantities, increasing the availability of airbags and vehicles. And then in 1994, the deep reactive ion etching (DRIE) is patented. So the DRIE technique was created by a Bosch, a German business. DRIE is a highly anisotropic etching method that is used to make high aspect ratio trenches, which is deep, steep-sided holes. Excavating trenches for high density capacitors for DRAM, which stands for Dynamic Random Access Memory, is another use. So in the late 1990s, which is early 2000s optics, Lucent Technologies created the first optical network switch in 1999. Optoelectric devices are optical switches. They are made out of a light source and a detector that generates a switch output. In a data communications network, the switch serves as a switching device. Micromirrors are used in the MEMS optical switches to switch or reflect an optical channel or signal from one spot to another. There are various design combinations to choose from. The advanced technology in this field is continually ongoing. And the last history of MEMS, which is on late 1990s, which is also early 2000s BioMEMS. Scientists are combining sensors and actuators with emerging biotechnology. Applications are included of drug delivery system, insulin pumps, DNA arrays, lab on a chip (LOC), glucometers, neural probe arrays, and microfluidics. Thank you.
Okay, next I will present about the application of MEMS. Application of memes are developed where miniaturization is beneficial, for example, consumer product, aerospace, automotive, biomedical, chemical, optical display, wireless and optical communication, and field. Okay, for specific application, for consumer product, means nozzle and pump for inkjet printer, radio frequency device such as switches, phase shifter resonator, filter and variable antennas, fuel delivery system that can control propellant motion, coating sensor that compensate for coating problem. Okay, for biomedical, medical MEM can consist of in vivo internal components and in vitro external components, such as this retina prosthesis. A microarray or retinal implant is implanted in vivo on the retina. An external camera and processor are mounted in a pair of glasses. Okay, MEMS pressure sensor. MEMS pressure sensor use a flexible diaphragm as the sensing device. One side of diaphragm is exposed to a seal reference pressure and the other side is open to external pressure. Okay, next is internal sensor, motion and shock detector, vibration detector and measurement of tilt and inclination, and anti-thief device.
Of MEMS is integrally linked to market trends in general and driven by the increasing demand to monitor and control our environment and the equipment and instruments we use in our daily lives. This demand does undoubtedly lead to the need for more sensors in cars, more sensors in industrial equipment and installation, and more sensors for our ambient intelligence. In order to avoid the need for multitude of wires, such sensors must be self-sustaining and able to communicate wirelessly. There is an increasing trend to spend on healthcare due to the growing number of elderly people in developed countries and in growing medical and pharmaceutical infrastructure in developing countries. There is also a trend to transfer diagnostics from the central analytical laboratory to a surgeries or clinics that are smaller and closer to the patients. This fuels a growing demand for small and affordable devices for diagnostics, especially for point-of-care diagnostics. In addition, national security is of increased importance related to the growing fear of terrorist attacks and outbreaks of infectious human or animal diseases. This drives a need for small multi-parameter instruments to test air, water, blood, and many more for microbiological threats. The so-called more-than-more trend will add new technologies to the rather monocultural landscape of semiconductors to enable extra functionalities. To explore further miniaturization by using die stacking. I'll proceed to the next slide. One general technology trend is especially worth mentioning: the increasing use of sensors and other small electronic devices in and around our direct environment. We will be surrounded by more electronics and will be interacting more with such intelligence. This creates a need for smaller and cheaper electronic products, which are energy efficient and self-sustaining as well as able to communicate via wireless with other electronic devices. Devices suitable for new applications connected to the ambient intelligence and ultimately expected to be used are smart dust. The big advantage of wireless sensor system is that by removing wires and batteries, there is the potential for embedding sensors in previously inaccessible locations. It also becomes feasible to use a large number of sensors because there is no longer the need for regular replacement or recharging of batteries. A shift from clinical to a point-of-care diagnostics, accompanied by a slow but significant drift from medical diagnostics to more lifestyle-oriented diagnostics, allergy, drugs, cholesterol, alcohol, but also diagnostics in sport. These together will make the market more consumer-oriented. The last 8 years, there have been more applications for registration of diagnostic devices than the 17 years before. Therefore, perhaps the fastest growing market for MEMS with many interesting applications for point-of-care monitoring, of which glucose level monitoring will represent the largest single segment. Cheap, these disposable sensors are regarded as the sweet spot in diagnostics. DNA chips have been commercialized by many companies, and a range of equipment is available for DNA chip sample processing, data analysis, and many more. Future lab-on-a-chip technology may include implantable pharmacy-on-a-chip devices precisely and timely releasing drugs into a body without needing needless needles or injections. The delivery of insulin is one such application, as is delivery of hormones, chemotherapy drugs, and painkillers. First-generation devices are being developed which release their medications upon signals from an outside source, wired through the skin. Proposed second-generation device may be wireless, and third-generation MEMS chips could interact with MEMS sensors embedded into the body to respond a body-owned internal signal.
So this is the end of our presentation. Thank you for watching our video presentation. So this slide is prepared by me, Sharina, and Muhammad Farhan bin Shahlan. And the information for the slide is prepared by me, Sharina, Farhan, Shahlan, Ruben Raj, Muhammad Azamuddin, and Nurul Afifah. Thank you.